Look down at the ground beneath your feet. It feels permanent, unmoving. But the rock you're standing on, and the silver moon hanging above it, were violently smashed together from floating cosmic debris. In the vacuum of space, high-speed collisions usually result in total obliteration. Objects shatter and disperse. So how did a chaotic cloud of shrapnel manage to engineer a perfectly stable planet? To answer that, we have to rewind 4.5 billion years. The starting line of our solar system is a swirling, collapsing nebula of microscopic gas and dust. Building a planet is an extreme survival test. Long before gravity could sculpt continents, only the most resilient microscopic matter avoided being completely destroyed. As the young sun first ignited, it flooded this early solar nebula with intense heat. The soaring temperatures vaporized almost all the available matter, turning rock and ice into a thin floating gas. This diagram shows a temperature threshold. While ordinary material disintegrates, a calcium-aluminum-rich inclusion, or CaI, holds its shape. These stay solid, acting as condensation nuclei. The heat-resistant grain collects surrounding gas, condensing into a hard rocky shell. Without these microscopic, heat-resistant seeds anchoring that initial mass, the building blocks of our solar system would have remained a swirling cloud of vapor. Once you have small pebbles, you hit a physical barrier, the bouncing problem. As these pebbles grow larger, the gas around them whips them up to higher speeds. When they collide, they don't stick. They shatter or ricochet off each other. To get past the size of a pebble, the early solar system relied on an aerodynamic workaround known as streaming instability. In this model, pebbles face a severe headwind of gas. This drag strips their momentum, trapping them in a dense cluster. Their collective gravity takes over, instantly collapsing the swarm into massive planetesimals. Our world was built by aerodynamic traps. The physics of the disk forcefully crushed all matter together before it had the chance to destroy itself. Fast forward a few million years, those massive boulders have crashed together to form a young, molten proto-Earth. This sets the stage for the most famous event in our planet's history, a collision with a rogue, Mars-sized planet named Theia. Under the traditional giant impact hypothesis, Theia strikes Earth, and the blasted-off debris forms the Moon. Logically, if an alien planet struck us, the Moon should be heavily composed of that alien impactor's material. But modern laboratory analysis reveals an isotopic paradox that completely breaks this traditional model. When scientists study actual lunar samples, like this one retrieved during the Apollo missions, they find that Earth and the Moon possess identical chemical and isotopic signatures. The oxygen and titanium in this rock are an exact match for what you would find in your backyard. This chemical identity demands a total revision of the giant impact theory. It suggests that the birth of our moon involved a process far more transformative than a simple collision. Enter the synestia model. Instead of a glancing blow that merely shattered the crust, Theia and Earth collided with such intense energy and angular momentum that the impact completely vaporized both planets. This diagram illustrates a synestia, a superheated donut of rock vapor where Earth and Theia thoroughly blended. Magma rains onto a molten seed inside, growing into the moon. As the cloud cools, it shrinks, reforming Earth with the moon in orbit. The Earth and the moon are not a parent planet and an alien satellite. They are identical twins, born from the exact same cloud of molten planetary vapor. In geological terms, this entire chaotic transformation happened in a flash. The synestia phase is estimated to have lasted just a single century, a cosmic blink of an eye. As the newly reformed Earth finally cooled, its materials separated by density. Heavy metals like iron sank to the center to forge the core, while lighter silicates floated to the surface, solidifying into the crust we walk on today. To verify this 4.5 billion-year-old sequence of events, scientists have to look beyond our planet. They need to find the original, unaltered building blocks that somehow escaped the extreme heat of the early solar system. That is why recent asteroid sample return missions, like OSIRIS-REx and Hayabusa 2, are so vital. Inside this metallic container sits raw, unvaporized cosmic material, the primitive ingredients of the original solar nebula. Bringing this material back to Earth allows us to inspect the raw chemistry of the early nebula, providing the physical evidence required to prove how our world was actually built. When you look up at the massive, quiet sphere of the moon in the night sky, you are looking at the direct descendant of those microscopic dust grains, the ones resilient enough to survive the ignition of the sun. The solid ground we take for granted is the final result of a violent process of condensation and survival. It is the end of a long, chaotic journey that began as a single grain of dust.